Hello, and welcome to the workshop on explaining and interpreting XGBoost models here at ODSC Europe 2020 Virtual. This is a pre-recorded video, so I am actually live with you on the Slack channel to answer questions and get everyone set up and working, but the video that you're watching is actually pre-recorded. But let's get started. So let's just first try to make sure everyone's all set up and ready to go with the code and the data. So the first thing you'll want to do is go to this GitHub repo, numeristical/resources, and either clone or download that. And then if you navigate to the folder ODSC Europe 2020, you'll find this notebook file inside of that folder. This is the title of it. ODSC Europe 2020 Interpretability. And then you'll use the link in the notebook to get the data set. So you'll want to click on that link, and you may have to go click on the download button, which is the arrow pointing down, to actually download the data set. And then once you download it, just make sure that you put that data file inside the ODSC Europe 2020 folder. And please check the Slack channel to see if there's any updates for the instructions in case anything has changed since I recorded this. Once you've got that set up, what I suggest you do is to make a copy of the notebook and then restart and clear that notebook. This way, we'll be going through the notebook together as if it's fresh, and you'll have the fully runged notebook in a different tab or in a different window to refer to if you have any problems or anything doesn't work. So I'm going to do that now. I'm going to click over here. I'm going to duplicate the notebook. I'm going to open up the copy. Wait for that to come up. And then I'm going to go over here, kernel, restart and clear all outputs. Okay. All right, so while everyone's getting set up, let me give a brief introduction about myself. My name is Brian Lucena. I'm a consultant, a researcher, and an educator. You could find out more about what I do at my website, numeristical.com. I work with a lot of startups, but also some larger public companies. I've started a YouTube channel on statistical machine learning, so I'd love for people to check that out. I think there's some really interesting content there that will be applicable to this audience. I've also developed 2 Python packages. One called ML Insights that we'll be working with today that has a lot of the functionality around model interpretability, as well as some functionality around probability calibration. The second package is called Structure Boost. It's pretty recent, and it's a package for doing gradient boosting with categorical structure. So categorical structure means that you have a categorical variable, but there's some relationships between the different values of the categories that you want to model. Structure Boost lets you model that structure. And that package is based on a research paper that I recently presented at the AI Stats conference just a few weeks ago. And you can find that research paper here, as well as a couple of other research papers on Structure Boost and Spline Calib, if you're interested in learning more about those. I'm also going to be doing quite a few talks in the near future. I'll be speaking at ODSC West at the end of October on Structure Boost. I'm doing a live training called Gradient Boosting for Prediction and Inference through the ODSC AI Plus platform, and that'll be on November 10th. And also talking at PyData Global 2020 on calibration, and the Data Science UA conference on Structure Boost on November 20th. So that's a little bit about me. Let's talk about the workshop and what we're going to cover today. So this workshop is going to focus on 2 main objectives. One is just overall how to understand your model and specifically your data. So one of the reasons you might build a model is to understand what's going on with your data, understand how the predictors relate to the target. And when you use something like XGBoost or boosting in general, one of the advantages is that you can understand more complicated dynamics in your data. And this often creates a challenge for people, because if you're used to just working in the world of linear logistic regression, you're used to models that are easy to interpret, but they're easy to interpret because they're a bit oversimplistic. They typically don't really have any interactions, and they're additive, meaning that kind of the whole is just the sum of the parts. And when you work with boosting, you'll start seeing that there are more complicated dynamics going on, more complicated relationships. But if you take some time, you can actually understand what's going on. And you can actually understand when there's something more complicated going on than those standard regression type models would allow you to incorporate. And we're going to go through an example and really understand how that works. Another concept I'm going to bring up over the course of this workshop is that of the coherence of a model. And when I talk about the coherence of a model, I talk about what's the story the model is telling. What are you learning, and how would you explain it to someone else? And the coherence of a model is important because if the story the model is telling just doesn't sound credible, then one, you should question whether it's really accurate, and two, you're going to have a lot harder time convincing someone else to trust your model. And what we'll see is that a lot of how the standard approaches to assessing your model don't really take into account the coherence. They typically, when people evaluate the model, they look at some performance metric like its accuracy or its AUC score. And if that number is good, they say this model is good. But in this talk, we're going to talk a little bit about how to assess the coherence of the model, how to understand whether the model makes sense and the story that it's telling holds together and conforms with our notions about reality. So that's the first part of the talk. The second part of the talk will be about how we understand and explain individual predictions from the model. So now I've got the model, I've got a particular case, and it's made a particular prediction, and I want to be able to explain in kind of human terms why the model thought this about this particular case. And we're going to talk about some approaches on how to do that. And we're going to use the SHAP package to get some of these reasons and to be able to do some manipulations and really explain what's going on behind the scenes so that when we have a prediction, we could attach some reasons to it that would make sense to another person. So let's get started in the notebook. So this first line is just importing a bunch of stuff. Hopefully it should all go through, and you need to have XGBoost installed. You'll also need to have the ML Insights package installed, so uncomment this line if you don't have it done already. And import ML Insights, and please make sure you have the most recent version, which is 0.0.1.5, and do an upgrade if you don't have that. And then once your data is in the proper folder, you should be able to run this cell and not get any errors. And you'll be able to load up this data. You'll see this data has 6,820 rows. This first variable called hasUmbrella, that's going to be our target. That's going to be about, does the person in question have an umbrella policy? So let me scroll down a little bit and give some background on this data. So this data set contains information about different insurance customers. So each row is an individual who has a home policy and an auto policy with a particular insurance agency. So we have information about their premiums, that's the monthly payments for each of those policies, how many different home policies they have, what's their coverages, which tells you kind of how much their house is worth and how much their possessions are worth, the number of cars they have, how old or young those cars are, the number of drivers, how old or young the drivers are, how old the policyholder is, and then some information about where they live, the homeowner's rate in the state, and then some zip code statistics about their household income in that zip code and the house value in that zip code. So broadly, it's information about premiums, coverages, vehicles, drivers, state of residence, and demographics in the zip code. And the goal in this exercise is going to be to build a model to try to predict who's likely to have an umbrella policy. And you can imagine that our goal is to be able to recommend to agencies which don't sell umbrella policies, which customers would be the best candidates. And so our binary outcome is going to be this variable has umbrella. So this is going to be a binary classification problem that we're going to work on. And we're going to focus on techniques for exploring, understanding, interpreting the data, and interpreting the models in this framework. So the first thing I always recommend people do if you're working with a binary classification problem, one early thing you should always do is to know what I call the baseline probability of your outcome variable, which is just what percentage of the case in your entire training data set is this thing true. So in this case, you see there were 6,820 data points, and just over 1,000 of them are true, so where the person does have an umbrella policy, and about 5,800 of them they do not. And if you look, it's right about 15% of people have an umbrella policy. And this is a really important number to have in context, because if the thing you're trying to predict is very rare, so for example, if you're trying to predict people who have a particular kind of cancer, let's say, which is very rare, and you found in a certain subpopulation that 15% of the people had this cancer, that would be extremely interesting and influential to know that. But if the general baseline probability of something is 15%, then it's not that interesting to find a subpopulation that's 15%. So it's really, this number, this baseline probability, really puts everything else into context. So in our case, it's important to know that, okay, starting out, 15% of people have, in this population, have umbrella policies. And to start, we're gonna try to build a model off of just two predictors to start. We're gonna look at their homeowner's premium and their auto insurance premium. And we're gonna explore how they relate to whether or not they have the umbrella. Now, if you don't know much about insurance, so premium is your monthly payment. So it's how much you pay every month to insure your house or your car. And so generally, if you have higher premiums, roughly you might expect that means the person has a more expensive house, and for auto, a more expensive car, perhaps. So we're going to explore to see whether this holds true. Also, I should talk about the umbrella policy. So the umbrella policy it's a policy that gives you extra liability protection. So it's something that people typically buy when they have more assets that they want to protect against, if they're at fault in an accident and someone were to sue them. It gives them extra protection against having their assets seized. So it's typically something you would buy if you have a lot of assets to protect. So let's start exploring these variables. So the first variable we want to explore is the homeowner's premium. And one thing I want to point out, this is kind of a pet peeve of mine, is if you just take a histogram of the homeowner's premium or of a variable in general without setting any bins, it's often going to give you something like this, which is not very informative at all. And this isn't useful for a few reasons. One is that the bins are really thick, and you actually don't even really know where the endpoints are because it's using some formula to sort of guess what are good endpoints. So what I recommend is always to put in your own bin width. So you could run this line first, and after I run this line, I see, well, pretty much everyone's between 0 and 10,000. So I'm going to make bins between 0 and 10,000. I'm going to make 100 bins. That's 101 points, so that each bin is exactly $100. And now when I do this histogram, you see, okay, this is much more interesting and much more informative. And in fact, if I wanted to, for example, if I want to know what's this highest bin here, I could just count from the left, 1, 2, 3, 4, 5, 6, 7, 8. So I know that this top bin is the one between $800 and $900 a month, or a year. I'm sorry, these premiums are per year. So anyway, this is, again, quick tip. When doing histograms, put your own bin widths and try to put a lot of bins so that you could really understand the shape of the distribution. And now the next tool I want to introduce is something in the ML Insights package, and I call it histogram pair. And it's a simple idea, but it's something you use when you have a binary outcome. So typically when you want to look at the relationship between two variables, you might do a scatter plot. If your target was numerical, when you do a scatter plot with something that's 0, 1, it's not very interesting to look at because you got a big band at 0 and a big band at 1, and you got to try to squint and look for something. So what this does is, I'll just run the cell and then explain it. What this lets you do is I create a set of bins. So in this case, the bins I've chosen, I did a few lines of code just to make bins that basically have width 250 up to 2,000, and then one more bin between 2,000 and 3,000, another bin between 3 and 6,000, another bin between 6 and 10,000. And now when I run this cell, I get two things. One is a stacked histogram, where the blue represents the zeros and the top part represents the ones. So for each bin, I can visually see the proportion that are 0 versus 1. And then I plot those proportions on a line here so that you can see that the proportion of ones starts out low. It gets bigger as we get to 500 and 750, actually goes down a little bit, and then starts growing again. And these error bars, you'll notice the error bars are kind of related to how many points are in the bin. So this rightmost bin, you see we have very few points in that bin, so it has a very wide error bar. Whereas the bins that are very tall have very small corresponding error bins. And the idea behind this function is to demonstrate the relationship between your target and your binary predictor. And it does it very empirically, just by looking at the data, and it doesn't presume any particular shape. So you might be used to using something like a correlation coefficient or something to try to assess this. But the problem with correlation coefficients is they really just measure the strength of the linear relationship. And so if your relationship is not linear, it's not clear how to interpret that number. Whereas here we see there's generally a positive relationship, although it seems to kind of go up and dip down a little bit before going up again. So this is an interesting relationship, and we'll dive into that further. But the idea is to demonstrate that there can be more complicated relationships than just a straight linear relationship. Next, let's look at the auto premium. So we're going to kind of do the same thing for the auto premium. Again, we do this first histogram. It's not very useful. We make a lot more bins, and we see a more interesting relationship. And then again, I'm going to do this histogram pair. And here we see, somewhat similar relationship, a little bit different. This one seems to keep going up for a while, then maybe drops down a little bit, and then again is high again. Again, this is just to give you a flavor. I wouldn't read too much into these, especially as these error bars are kind of big over here. But what you should get out of that is it's certainly not just a straight linear relationship. It seems to be generally increasing. It might dip down a little bit, but it's certainly not linear. But it certainly has a lot of information. And we could, in theory, do this for all of the variables to understand them. For now, we'll just focus on these two variables. But if you really wanted to dig into your data, you might want to actually do this exploration on every single one of your variables to really understand what the marginal relationship between your predictor and the target is. So now let's start building a model. And another good practice when you're building models is to build a model on a small number of variables first, just to get a sense of behavior. So pick a couple of variables that you think are going to be important and see how well you can do with just those couple of variables. Because often what you'll find is that when you're building a model, it's really 2 or 3 variables might be giving you all the predictive power, and everything else you add just marginally improves it a little bit. And that's an important thing to understand about your data set and about the world that you're working in. So I have folds already programmed in to the data set. So what I'm going to do is there's fold numbers 0, 1, 2, 3, and 4 that are equally sized. And I'm just going to say we're going to use 0 as the test fold and the other folds as the training folds. And my first set of features is going to be just this auto premium and the homeowner's premium. And the first question I'm going to ask is, given this chart here, so if we look at these bins, what we see is, so even the people with the highest homeowner's premiums, about 30% of them have umbrellas. And remember, on average, about 15% of people have these umbrella policies. And likewise, when we look at auto, we see this number goes up to about 20%. So one thing to think about is, given just these two variables, how high can we expect our precision to get? Meaning, when we have the people who are the most likely to pick umbrella policies based on just these two variables, so they have a very high auto premium and a very high homeowner's premium, how high should that precision expect to get? And just think about it. Guess for yourself a number, and then we're going to go through and see what actually happens. So we're going to define our training and test sets. So I just use these fold numbers to define training and test sets. So we've got an 80% train and a 20% test, because I picked 4 folds to be train and 1 fold to be test. And to get started, I'm just going to use XGBoost with whatever the default settings are. So I'm going to define my XGBoost classifier. Again, just use the default settings. I'm going to fit the model to my X and Y. And then I'm going to predict the probabilities out. And the next question is, how should we evaluate this model? And common things I like to use for binary classification are things like the AUC score, the log loss, and precision recall curves. And I'm not going to go into too much detail. If people have questions about it, I'm happy to answer questions on Slack. If you have questions about what those metrics are and why I like them and so forth. But for now, let's just look at what they are, look at the values. So you'll see I get an ROC score of about 0.56, which, 0.50 means there's no relationship at all. So it's not a very strong predictive performance we're getting in general. And if we look at this precision recall curve, you'll see, so the question I asked was, how big does your precision get? And you'll see our precision, we're able to get about maybe 0.35 or so precision at recall, about 10%. So that means we take this group of people that look most likely to buy the umbrella policy. They have a probability of about 0.35, whereas the baseline probability is 0.15. So they're a little more than twice as likely as the average person to buy an umbrella policy. And depending on your problem, that might be very good. That might not be very good. But the key is, if you look at our marginal relationships, this is not surprising, right? Because the homeowners kind of maxed out at around 0.3. Like the people with the biggest, most expensive homeowners policies, about 30% of them had umbrella policies, and that was kind of a small group. And with the autos, it maxed out even lower at like 0.2. So you've got two different signals. One makes it about twice as likely as average to buy a policy, and this auto premium, if you're really high, you're just a little bit more likely, 20% versus 15%. So when you put them together, what happens is the model kind of concludes, okay, if you're really high in both, you're getting to about 0.35-ish as your predicted probability. So when you do this, you get some sense of how the models work, and this is probably how most people approach their model evaluation. But what I want to bring up in this lecture is some other less utilized but still very important ways to examine your model. And the first thing I'm talking about is calibration, which we can assess via what I'll call a reliability diagram. And calibration essentially says, when my model predicts 20%, does it really happen 20% of the time? So are these probabilities really behaving like probabilities, these predicted probabilities? And the way you check this is you look at the test set and you find a bunch of places, let's say, where the model predicted a probability between 0.19 and 0.21. And let's say you find, 200 instances of that. Well, I find 200 such instances. If the true probability is really 0.2, I should expect about 40 of them to be true. And you look at the fraction that actually occurred, and then you could determine whether your model is well calibrated. When it says 20%, did it really happen 20% of the time? Did it happen more like 10% of the time, or did it happen more like 30% of the time? Was it overconfident, underconfident, and so forth? So that's the first tool we're going to use. It's called calibration. And then we're also going to look at what are called ice plots, which is, let's say I take a point in my data set, and then I change just the value of one feature. How does the value of my prediction change? And we're going to sort of take a subjective look at that and say, is this coherent? Does the story the model is telling hold together? Does it really make sense what the model is suggesting? So let's start looking at the data. So the first thing we're going to do is look at this reliability diagram. So again, what did I do here? I took a bunch of bins of different sizes, and I used a test set. So I'm using my Y test here. And I'm saying, okay, on the test set, when the model predict a probability in a certain bin, was the actual percentage of time it was true close to kind of the average value in that bin? So, for example, if I look at this bin here between 0.2 and 0.3, you see we have a bin here, and we had about 100 and call it 120 or so different cases that where my model predicted between 0.2 and 0.3. And that corresponds to this point over here. I can't show you, but the bin right after 0.2, and you'll see the dot is a little bit below the line x equals y. So what that means is that the probability, the actual probability, was a little bit less than what we would have expected given the model's probabilities, but it's between the error bars. So it means that it's kind of within normal variation. So if we look at this reliability diagram, and if you've never looked at these, it's going to be hard to get a sense of it. Is this good? Is this bad? What am I looking for? But we're going to look at a few of them, and I think as you look at a few different ones, you'll start seeing different patterns. But one thing you're looking for is points that are outside the error bars. So here, if you see this fourth bin, the dot is just outside the error bin. So just one like that isn't so bad. But also, I think this first one also seems to be a little bit outside the error bars. And again, the easiest way, as we see future ones, I think you'll start seeing more patterns as to like, oh, this one looks really good versus this one looks off. But this is one way to judge just, are my predicted probabilities really behaving like probabilities? If you see a bunch of dots way outside the bins and they're constantly above the line or they're constantly below the line, then you know that your model is not well calibrated. The next tool I want to bring up is this ice plot. So the idea behind this individual conditional expectation plot is that we hold all of the features constant except for one. So we start with a data point. So in this case, we have someone, let's say they're spending $1,000 for their home policy and $2,000 for their auto policy. And then I say, what happens as I change what they paid for their home policy between, let's say, 0 and 10,000? If I just change that one variable, hold everything else constant, how would my model change its predictions? And this is going to be useful in a few ways. One is that you could see how the model changes its prediction with respect to that one variable. And you can also see whether the shape of that curve is consistent. And that will tell you about interactions. So let me go and show one of these plots really quickly. So for a single feature, so this is the ICE plot for just the auto premium. And you'll see what this says is this black dot shows the true value. So this blue curve, this black dot represents 1 point where the actual auto premium was, say, about $1,200. And what the blue curve represents is what would the model have predicted for this particular data point if I changed the auto premium value, if I put in a different auto premium value. So you'll see if I put in a smaller auto premium value, this probability would drop pretty quickly. And if I got it bigger, you see a lot of spiking and jumping. And what that means is that this model seems to be very sensitive to particular values of your auto premium. So it actually thinks, the model thinks that, I'm going to go up, and then I'm going to go down, and I'm going to go up, and I'm going to spike up and down a lot as my auto premium increases. And you can ask yourself whether that makes sense or not. And this is, again, another way to assess a model and assess the coherence of the model. What's the story? The story the model is telling is like, actually, the very specific changes in the values make a big difference in terms of the probability someone's going to buy an auto policy. So if they're spending $1,250 for their auto premium, they're going to buy it 20% of the time. But if they're spending $1,350 on their auto premium, their probability of buying a umbrella policy is going to drop down to 15%. And you can ask yourself whether you believe that or not, or whether perhaps it's just overfitting or finding some spurious correlations. So this is a useful tool. One thing I want to back up and show is the ICE plot definition. I don't have time to go through all of these things, but this ICE plot function can do lots of things. It can show multiple columns at the same time. You can give it the range of things that you want it to plot. So you can adjust lots of things on these plots, and we'll walk through by example some of those. So this is how you do it for just a single plot. If I wanted to do for all the variables, I would do this thing called get range dictionary. This is just going to take a guess as to what a reasonable range of values is for each of your variables. So you see it's just a dictionary that maps the column name to a NumPy array of possible values. And then I can make an ICE plot for all of the columns. In this case, it's only 2. But again, the main thing I want you to get out of this is that this is very spiky. And spiky is usually bad and not very coherent, because we don't really expect that as I pay $10 more for my auto and homeowners and premium, that it should make me go up and then go down and then go up and then go down, and my probability should change wildly. We would expect something sort of smoother, and maybe there's certain values where it really slopes up or really slopes down, but we don't really expect sort of wild spiking. Now this next cell is just to demonstrate if I make this ICE plot. Let's say I really want to focus in between 0 and 5,000. I don't want to see this stuff out here because I don't have a lot of data out there. I can use my own ranges by updating this dictionary that I passed to the function. So I just update the dictionary with what I want the range of values for it to plot. And now you see now I'm just focusing in between what happens between 0 and 5,000. But again, we see a lot of spikiness, and in general, spikiness means that it's probably overfitting. And the key is that this is overfitting, but you wouldn't know that it was overfitting unless you really chose to look at this plot. And most people don't look at these plots. They just look at their overall number, and your overall number could look fine. Your AUC score might look fine, or your log loss might look fine, and you can't really tell that your model has such an erratic behavior unless you look at something like these ICE plots. So to give a comparison, let's build a second model, and let's do a bit more regularization. So instead of just using the defaults from XGBoost, we're going to do a few different things. One is we're going to use an evaluation set and early stopping. So this is an approach that I strongly recommend when you're doing a boosting model. One of the parameters you have to tune is how many trees to build and when to stop. And a good way to tune that is to just look at the performance on an independent test set and say, as the performance is getting better, I'll keep going. But once my performance starts getting worse on this independent test set, I'm going to stop. And there are a few ways to tune that. When you use an evaluation set and early stopping, one advantage is that you can then just use a very low learning rate and a high number of trees. So you could just say, take very small steps, and then I'll know when to stop. I don't have to use all, in this case I said to 1,000, but we're not actually going to use all 1,000 of the trees because we're going to stop before we get to the end, probably anyway. Another change I made, I used a smaller max depth. So I used a max depth of 2. Again, smaller max depths tend to be more regularized, less likely to overfit. I added in some subsample, so I'm going to vary the subset of data that I run this on every time. Again, that also adds some regularization because it's not as easy for the model to fit to some noise in the data if the noise kind of changes a little bit at every iteration. And I'm going to use this gamma and this reg lambda. These are also regularization parameters, what are called kind of shrinkage parameters that also help to regularize the model. And the upshot is I'm going to run this model, and if you compare this second model, what I call complex 1 versus default 1, it's not really a huge difference in sort of the numerical metrics. And if I look at the precision recall curves, again, not really a big difference in the performance. So our numerical indicators of the performance of these models is that they're really about the same. But now what I want to show is, let's look at some of these other things that we talked about, the calibration, the reliability diagram, and the ice plots, and see if those show a difference between those two models. And so if you look at this reliability diagram, I think you'll see that, you'll see a few differences between this one and the other one. First, almost all the points are really, really close to that y equals x line. So this is really well calibrated, much more so compared to the previous one up here. Right here they were jumping around a little bit, and these last 3 ones I wouldn't worry too much about because the error bars are really big. But even these earlier ones where we had a lot of data, the numbers, the points are jumping around a bit more. Also, if we look at the range in this old model, the range of values, predicted probabilities, was spread out a lot more. Whereas for the one we just did, it's a little bit tighter, right? We never predict anything above 0.4, and we never predict anything below kind of 0.1. So that's another indication that this model is doing a better job of not overfitting. It's not trying to be too confident. It's sticking pretty close to 0.15. Remember, 0.15 is our baseline probability. And we're sticking pretty close to 0.15 and only going out a little bit from that in our predictions. It's being a little more conservative. Now let's look at the ice plots. And here we see a big difference, right? This is telling a very simple story now. For auto premium, it's saying, you start having a big change in your probability of buying a umbrella policy around $1,000 in your premium, and then you level off. And for homeowners premium, it's a little bit more complicated. You seem to go up for some of these early numbers, and then down, and then up again. But again, this is a sort of simpler, more believable story. I don't really know what's going on, why it goes up and down here, and we're going to find out about that later. But it's plausible. You can imagine a few different explanations for it. But it's really a simple story. It's up, down, and then up again. Whereas when we looked at the other one, this was not telling any sort of coherent story. It really just seemed to be just wheeling around wildly. So, I would ask the following questions. Of these two models, even though they had very similar scores in our performance metrics, of these two models, which looks more coherent, which tells a story that you believe? Which model would you feel more comfortable justifying to your boss and clients if you're trying to explain how the cost of someone's premium relates to their probability of buying an umbrella policy? Do you feel more comfortable kind of saying, well, auto premium, it's low, and then it starts going up once you cross around 1,000. And for homeowners premium, there's something weird going on, but basically it goes up for small values, then it goes down, and then it goes up again. And another question: which model will provide a better user experience? So remember, there's someone at the end who's going to be seeing the end results of these models, and inevitably, if you have a model with a really jagged performance like that first one, inevitably someone will say, "Hey, these two people are exactly the same, except this one's paying $10 more for their auto premium than the other one, but they have wildly different predictions. One's 15%, the other's 20%. Why does a $10 difference in the auto premium make a 5% difference in their buying an umbrella policy? It just doesn't make sense." So the end user of your model will not trust the model very much if it's not coherent. And also, which model do you expect to generalize better to new cases? Remember that when you're training, you're only judging the performance on the cases that you've seen already. And what you want is something that's going to generalize well to the cases you haven't seen, that it hasn't been scored on. And in general, if a modeler has a simpler, more coherent explanation, it will generalize better. But also, at the same time, notice that these explanations of this model, while simpler than the very jagged ones of the first model, are still sophisticated in that there's interesting relationships going on here. So we can capture models like boosting, used correctly and explored correctly, can yield interesting dynamics of the data that you can then try to explain and justify and bring your domain expertise to shed more light on. So the one question I want you to think about is, what's going on with this homeowner's insurance? What might be going on here that would account for this bump up and down? And we're going to find the answer out soon as we go forward. So next we're going to add in the average homeowner's rate in the state. So one thing about insurance is that it's regulated at the state level, and every state has different regulations, different things you're required to cover, different things you're not required to cover, or maybe different minimums and so forth. So these change how much homeowners insurance costs in different states. Another thing also is different states will have different levels of, let's say, natural disasters. So if you're in an area where there's a lot of hurricanes, it's going to be a lot more expensive than in a place that doesn't have those natural disasters. And so we're going to try to so what does that mean? That means that if I'm paying $1,000 in Nebraska versus paying $1,000 in Florida, that's going to mean different things. Florida actually has a very high homeowners insurance rate because there's so many hurricanes and so forth. So $1,000 premium in Florida is actually kind of a cheap premium, means you probably have a very inexpensive house. Whereas an $1,000 premium in, say, Nebraska might mean you have a more expensive house. So let's see what happens when we add in this feature, which is the average homeowners rate in the state. And we're going to train the same model we trained before, just with this extra. So this is the complex model with this one added feature. And wow, what do we see? We see that the performance increases, dramatically. So we now have an ROC score of 0.81, which is good. It means it has pretty good explanatory power. Log loss dropped a lot. And the precision recall curve, you see, wow, we're now able to predict, up to 0.6 precision, quite high. So you see this curve has shifted dramatically to the right, meaning dramatically higher precision across all values of recall. So what's going on? Again, looking at these metrics, we can see that this homeowners rate is important, But without diving deeper, we can't really understand what's going on. So we'll look at this calibration, and we see the calibration is pretty good. Everything's pretty much within the error bars. Maybe this one's a little bit off, but roughly pretty good. Now let's do the ice plots. And here now we're starting to see something very interesting. The first is that our homeowners in premium, the ice plots are now always increasing. So we got rid of that bump, whereas before we had that bump up and down and up again. Now that we are controlling for the average homeowners rate in the state, we're actually saying, have a model that says, no, as you pay more in premium, you're more likely to buy an umbrella policy. So let's try to understand what's going on. What was going on before in this old model was, since we didn't control for state, as you paid, if you were paying around this value, it was saying, well, if you're paying around this value, you probably live in a state with low insurance rates. So in kind of this range, the top of this peak was kind of actually people with kind of expensive houses that lived in low insurance rate states. And then as the insurance rate got bigger, it said, oh, well, now the model thinks that you're probably you probably have a cheaper house in a higher risk state. And then as your premium increased even more, it said, okay, now I think you probably just have a more expensive house. So that's what was going on here. And that's sort of the missing piece of this explanation, was that as you progressed across this premium, you were getting a mix of different states. Certain states were represented more than others, and different income groups in those different states. And so now, since we added the homeowner's rate to the state, now when the model's changing the homeowner's premium, it's holding the state fixed. So it's saying, given that you're in this particular state and you're paying this particular auto premium, as I increase your homeowner's premium, what happens to your probability of buying an umbrella policy? And now we see that it's always increasing. So this should give us comfort. This makes us is a more coherent model. This makes sense now to us more, whereas before we couldn't explain that bump. Now we don't have that bump anymore. The other thing we see is that, again, states with lower average rates are more likely to be buying an umbrella policy. And if you think about it, that makes sense, because the lower rates means that your premium is relatively worth more. So again, the Florida-Nebraska example, that same premium in a lower risk state indicates a higher value property. And you see there's a little other bouncing around here, and that might be just more state-specific regulations. There's a little bit of noisy stuff going on here. So it's not just about the rate in the state. There's probably also some state-specific peculiarities going on here as we add in this number. But, as we can see, the model is done much better, and the explanation now makes a lot more sense. Now, if we look at auto premium, we see something interesting. One thing that's interesting is that it's mostly going up, but then at the end, it seems to dip down a little bit. And having worked in the space, I can tell you what's going on here. What's going on with that is that auto premiums are largely reflective of things like age, the value of your car, stuff like that. But when you have a very high auto premium, that's typically an indication of a very poor driving record. So whereas at the beginning, higher auto premium means that you're maybe more likely to have a nicer car, at the end it just means you're more likely to have had a poor driving record, which doesn't necessarily make you more likely to buy an umbrella policy. Okay, so next we're going to add in a lot more variables. We're going to kind of throw in the kitchen sink here and see what happens. And again, we're going to fit it. let this all run. And you see, okay, we're definitely improved. Our model is definitely improved. Our AUC score went up to 0.845 from 0.811. Log loss went down. Precision recall curve moved to the right. But, you know, we didn't improve as dramatically as we did from just adding in the context of the state. And that, again, that kind of makes sense. You know, it's typically very few variables account for most of the power of the model. But now, even with this model with lots of variables, we can start getting a sense of what's going on with the model. Again, we can look at the calibration. Calibration looks pretty good. We see also a wider range of probabilities that are being predicted, but when it predicts these higher probabilities, it's accurate. So it's predicting 0.75 on a lot of people, but when it predicts 0.75, it is actually about 75% of those people are buying the policy, so that's good. Now let's look at the ICE plot. This takes a couple seconds to run. So now we see some really interesting things. So let me walk through some of these explanations. So one big change from the previous model is that now the homeowner's premium essentially is meaningless in this model. And the reason why it's meaningless is because we actually have the home dwelling coverage, that's how much the house is insured for, and the home personal property coverage, how much the contents of the house are insured for. And basically, these numbers are much better indications of wealth than the premium is. So the home dwell cov and the home pers prop coverage are really how much your house is insured for. It's really a better indication of the value of your house and the value of your possessions. And the premium was kind of a much weaker indicator. So now that we have these stronger indicators of wealth, this weaker indicator of the homeowner premium actually doesn't mean anything. It's not useful to the model. It's really focused on your dwelling coverage and your personal property coverage. We see that this is the year of birth of the policyholder, YOB policyholder. We see that seems to be an important one, and it goes down with the year of birth. So as you go down, as your year of birth goes up, that means as you get younger, you're less likely to buy a policy. So as you get older, you're more likely to have the policy. Auto premium, we're kind of seeing that same effect here. It goes up and then it goes down a little bit for the most expensive policies. The vehicle year, so how old is your car? We see that if your newest car is pretty new, you're a little bit more likely. It's not a huge effect, but we see people with newer cars tend to buy umbrella policies more. That makes sense. People with newer cars tend to have more money, have more assets to protect. Number of vehicles, don't see a huge difference, but there does seem to be a little difference between having one car and two cars. And then after that, it's pretty flat. The ages of the driver, so the max driver year of birth, that's the age of the youngest, that's the year of birth of the youngest driver. So as we go to the right, means you have a young driver. And you see this starts to kick up a little bit right around 2000. And this data set's a couple years old, so it's around 2018. So I think this is picking up on, it's a very small effect, and I might be reading too much into it, but I think this might be picking up on people who have teen drivers. You might be more likely to buy that extra liability insurance when you've got a teen driver at home. And then we see these demographic factors. So this is the median household income in your zip code, the median house value in your zip code. And we see that these are also important factors. And the state, again, ends up being a very important factor because it gives context to so many of these other variables. Okay. Now, again, let's compare to what this model would look like with the same variables if we just use the default settings. So you'll see we get around the same performance. Calibration still looks okay. But let's do the ICE plot. And you'll see it looks okay, but we still have a lot more of these little jiggly things. So if we look at the home personal property coverage, which is the the second row, first column, and you look at this top curve, we see that, like, you get this drop down and then drop back up, this little spike down. So we're still, these are a little bit more spiky than the other ones. Homeowner's premium, we see a little spike up at the beginning of the curve. Max driver year of birth, again, we see this weird kind of spiky behavior. So again, because we have less regularization, these models are a little bit less coherent. They have a little bit more idiosyncratic behavior that we don't necessarily believe, where it's probably overfitting to some degree, but we're just not catching it because our metrics aren't good enough to catch it and our data is not full enough to force the model to correct those idiosyncrasies. Okay, so that's going to be the end of part one. And the summary is model understanding is still possible, even when your models are more complex. It's important to broaden your thinking beyond the assumptions of linear and logistic regression. The effects of a variable are not constant across its range of values, so we saw that, a lot of non-linearity. And we also saw that the shape of the response curve might vary depending on the values of other variables. There might be interactions. But we can still explore and understand these. Now we're going to move forward into part two, running behind on time a little bit. But in part two now, we want to understand the reasons behind a specific prediction. So in this case, my model said this person is very likely to buy an umbrella policy, and we want to explain why we think that person is more likely than average to buy an umbrella policy. So our goal is to explain why a particular instance is different from average, and which features and concepts contributed most to its distinctiveness. And what we're going to try to do, and what we're going to do with the help of SHAP, is attribute the distance from average of a particular case to individual features. So the concept of SHAP comes from the Shapley value, which is this idea in game theory. And the way it's going to work in our model is the following. Suppose I randomly ordered the features. So I start out and I have a person, and you ask me, what's the probability they're going to buy an umbrella policy? And at first I don't know anything about them. So I just say 15%, because that's my baseline prediction. I know 15% of the people in the data set bought umbrella policies. I don't know anything else, so I'm going to guess 15%. And then you tell me, well, this person is 60 years old. And my model says, okay, well, if I were going to look at a model and just use the age, if I just knew they were 60 years old, knew nothing about them, then my probability would go up to 25%. So you'd say, okay, so age counted for a probability increase of 10%. And then I say, well, what if I told you they lived in this zip code where the median income is kind of low? And I would say, okay, if I know the age and I know the zip code demographics, now my probability goes down to 20%. So I kind of got a plus 10% for the age and a minus 5% for the zip code. And I do this incrementally for each variable. So each variable gets kind of credit for the change in probability it brought. But now that change is going to depend on the order in which I learn the variables, right? So for example, if I have two redundant variables, the first one will get credit for telling me something. And then the second one didn't really tell me anything different, so it's going to get kind of a 0. So every time I do this process, every time I have a different ordering, the variables are going to get credit for different kinds of changes. And the idea is that if we averaged over all possible orderings, we would this would give us a reasonable assessment of how this variable impacted my prediction. And that's, again, comes from the Shapley value. And so what we want to do is average the attributions to a feature over all possible orderings. So I play this game for one ordering, then I'm going to pick a different ordering, do it again, and try every single possible ordering and say, on average, when I learn their age at whatever point in this process, when I learned the person's age, how much did that influence my prediction? And we're going to attribute that value to age. So, if you're interested, I recommend learning a little bit about the Shapley value. So one famous use of the Shapley value in game theory is that if you use it to analyze the UN Security Council, so the UN Security Council has 5 permanent members and 10 non-permanent members. The 5 permanent members have veto power. So to pass any legislation in the Security Council, you need all 5 of the permanent members plus at least 3 of the other 10. And so you could think about this as saying, what's the probability that if I randomly order people, at what point does a country become kind of the swing vote? And if you do this analysis on the Security Council, you find that basically 98% of the power lies with the 5 permanent members, that basically the other 10 members have very, very little power, and pretty much all the powers in the 5 permanent members, which makes sense, but it's nice that it actually is able to quantitatively assess that. So this is a lot of theory and stuff. At the end result, what you want to say is, for each feature in our model, we're going to do this process, and what this feature is going to say is kind of, on average, learning that this feature had this value increased my probability by this much, or decreased my probability by this much. So let's get into how to do this. So I'm going to take my last model, and I wrote a little function called get reason score matrix. The function is basically these 3 lines below. But let's see what it does. So when we run it, what this now does is it says, okay, each row is a particular item, data point in my test set. And so for this particular data point, when I learned their auto premium, that made me think they were more likely to buy an auto policy. Their homeowner's premium made me a little bit less likely to buy it. When I learned their home dwelling and personal property coverage, each of those made it much less likely that I was going to buy it. So the negative numbers means when I learned this value on this data point, it made the model think I was less likely to buy an insurance policy. If it's negative, and if it's a positive number, it means it's more likely to buy it. So let's get into some details. So the idea is that one change from what I said before, we're actually going to operate on the log odds scale. So when I talk about the change in probability, what I actually mean is the change in the log odds. And that's just like a scaling issue, but it's an important thing to keep in mind. So I'm going to work on this log odds scale, and all these numbers are with respect to the log odds scale. So if we look over here, we see my intercept is minus 0.187. And what that means is this is my baseline. So the log odds of a probability of 0.15 roughly corresponds to a log odds of minus 1.87. So this is where I started. And then these numbers for each feature give us how much adjustment to make for each feature. And so if I sum up these feature values across the row, including the intercept, I'll get the overall log odds. And that's what this little calculation is going to show. That essentially I'm recovering the probability by adding up the log odds of all the pieces. Let's jump into a specific case. Hopefully this will help explain some of what we're doing here. So, I'm taking a particular row. So this is a particular data point, and I've rearranged the values in order of their feature importance. So what this means is that this person has a home that's insured at $760,000, and their personal property is valued at $380,000. And learning these were strong factors in my model for believing that this person would buy an umbrella policy. The auto premium was a slight positive. Learning that their newest car is in 2018 and that their second newest car, or that their oldest car is in 2017, so they have relatively new cars, that also made me more likely to think they were buying an umbrella policy. The things that made me less likely to think they were going to buy an umbrella policy were the median house value and the median household income in their zip code. So they actually live in a zip code which is not, appears to be not super well off. And so when I learned their zip code, I said, this makes me think they're less likely to buy an umbrella policy. But then when I learned the actual value of their house, that overwhelmed that and made me think they're very likely to buy it. So this is an example of how we can attribute strengths to each of these features. We can see which ones were positive, which one made me more likely to think they would buy an umbrella policy, which ones were less likely to make me think they would buy an umbrella policy, and the relative strengths of those features. So what can we do with this? We could also look overall. We could say, in general, this was for one particular case, but if I average these numbers over all the cases, and I average the absolute values so that what's important is being far from zero, having either a positive or a negative impact, I can sort the values and get a sense for what's going on with these. And what you'll see is actually knowing the state ends up being very influential. But then the next most influential ones are the value of their personal property was insured for and their home dwelling coverage. So basically how much their assets are insured for were the next two most important things, followed by the median house value in the zip code, the age of the policyholder, then the median income in the zip code. So it's interesting that the house value of the zip code is more important than the median income of the zip code. Then the age of the youngest driver, how much they paid for their auto premium, and so on. And the least important thing now is the home ownership premium. We could also take these reasons and look for the correlations between them. So this is just something to play around with. And you know, one thing you'll notice, so for example, this 0.46, you'll see that the home dwelling coverage is related to the median housing value. Well, that makes sense because if you live in an area where the housing values are high, you're more likely to have your home insured for a large amount of money. But again, these are all just ways, these are now tools by which you can look at individual predictions and really get a sense of which features are contributing to those predictions, positively or negatively. Here's a little plotting function I wrote to analyze the effect. So I want to see what's the contribution of the year of birth to the score. And you see it ranges. So for example, for people born before, let's say 1950, knowing their year of birth ranges from kind of a 0.1 on the log-odd scale to a 0.4 on the log-odd scale of impact in terms of how likely I are to do it. How much more likely does this make me think that they're going to buy an umbrella policy? And what's interesting is you get a range of possible values, and this is where interactions come in. Interactions mean that your how much this variable influences my prediction depends on some of the other variables. If knowing someone is 70 years old always had the exact same impact, like in logistic regression, without any interactions, then I would always have a straight, I wouldn't have any up and down variation here. Knowing 1950 would always mean the exact same value here. But here, knowing 1950 gives me a range of possibilities depending on other things I know about this person. Similarly, median household income of the zip code. So again, when I learned that you live in an area with median household income of 50,000 or less, that's a negative factor, and it could be anywhere from like a pretty significant negative factor to a small negative factor, depending on what else I know about that individual. Okay, running out of time here, so I'm going to try to go through the rest of this stuff a little bit more quickly. Now, as we saw, let me scroll back up for a second, look at these reasons. So if you were trying to make a product where you're trying to explain to someone why you think this person is likely to buy an umbrella policy, telling them about the home dwelling coverage and the home personal property coverage and breaking out into this level of detail might not be very user-friendly. It might not be something they want to think about. You might want to, but a lot of these things are related, right? So for example, the home personal property, the home dwelling coverage, they're both talking about how much real estate this person owns. The median household income, the median house value, we're talking about where the person lives. So one thing that's useful is to try to consolidate, take a bunch of features that are all related to some category and consolidate them. And from that, you could get much more simple, much more meaningful reasons. So here, we create a little dictionary, and we've basically taken all of our features and consolidated them into four or five categories. So the value of the real estate, which has to do with the premium, the coverages, and the number of homes they have. State-specific factors are just the average homeowner's rate in state. The value of their cars, which is about how old the cars are, how many cars they have, and how much they pay for their auto premium. The age of the policyholder in the family, so that's how old the policyholder is and the ages of the drivers. And then the zip code they live in, how wealthy is the neighborhood they live in, which is about these two variables. So if I essentially just sum up the component reason scores into these groups, just aggregate them, I now get a much simpler set of reasons. And now when I take an individual, and so here's someone that we think is not likely to buy an umbrella policy. And if they say, why do you think they're not likely to buy an umbrella policy? You could say, well, they scored low for the value of their real estate. They scored low for the zip code they live in. They scored low for the age ranges of the policyholder and the family. And now again, if we look at the average impact of these variables, now you see real estate is the most important, followed by the state-specific factors, then the zip code wealth, then the age of the policyholder and the family, and then the value of their cars. And again, this gives a good sense. This gives a nice big picture also of what the model is looking at. Or basically, if somebody says, what's in the model, what are you looking at? You could basically say, well, a lot of it's just about how much real estate they own. A medium chunk about what zip code they live in. And then, some adjustments also for how old the person is and their family is, and how much their cars seem to be worth. And again, you could do these correlations. You see the zip code wealth is correlated with the total value of real estate. That makes sense. It's not that much. I guess the one slight negative correlation is in the age of the policyholder and the value of the automobiles. So actually people who are more likely to buy because they're in the right age range are actually less likely to have expensive cars. Now again, to make this sort of more usable, we can actually come up with something now where you set a threshold and you say for each prediction, I'm going to include the reasons that scored above a certain threshold. So for example, and let me make one quick adjustment here. Well, let me not do that. So in 24 of the data points, we found that the reasons we would have given were that this person has a lot of real estate and they live in a wealthy zip code. And that's the most common reason. For a lot of people, we would just say based on their state and their zip code. For some people, it would be all three. But this is a way, again, if you wanted to attach meaningful reasons to each one way to do that is you consolidate these reasons, you get values for each one, and then if they exceed a certain threshold, you say this was a significant reason for the model. So rather than giving people the numbers, you could just say, I'm just going to give you the numbers that exceeded a certain threshold. Now let me go into the SHAP package. The stuff I just showed you before was before the SHAP package was really built out. And now since they've built out, they have some cool functionality, which helps. So if you need to install the SHAP package, if you don't have it already, and hopefully this works. There's a JavaScript thing here that may or may not work on individual machines. But the SHAP package now has built in some stuff. And one cool visualization they have this thing is this, what they call this force plot. And the way to interpret this, I don't love the way this is set up, but the way to interpret this force plot is this base value. You see the word base value there. The base value indicates on the log odds scale, what's my baseline probability? So remember we said 15% was about like negative 1.87. So that's where we're starting here. And then for this particular individual, our predicted probability on the log odds scale is about negative 0.48. So it's about negative 0.5, so it's a little bit less. Let's say it's around 40%, give or take. So what this means is when I didn't know anything about this person, my probability was around 0.15. And when I learned everything about the person, I ended up at about 40%. So kind of how did I get there? And the way to think about this is these red bars show me what factors made me more likely. And these blue bars show me what factors made me less likely. And if I take the full length of all those red bars and then subtract out the length of those blue bars, I'm going to get exactly the distance between the base value and the model output value. So you could think about it as I started with the base value, I added in all these red bars that pushed me past the true value, but then the blue bars kind of pushed me back to where I landed, which is at negative 0.48. So again, it's a nice visualization. And again, the bigger the bar, the more impact it had. So you see the big bars correspond to these, the value of the home is insured for, and the value of the assets. Now, if you combine this with consolidating the reasons, you can see now for the exact same data point, when I consolidate the reasons, I get a much simpler explanation. I get the value of the real estate was really this very huge reason for it. Value of the automobiles was secondary, and the zip code wealth was actually kind of an offsetting negative value. And everything else was relatively minor in comparison. Okay, we're getting near the end. So the last thing I just want to show is this, these interaction values for SHAP value, and try to explain them and try to show what I thought was a kind of a cool example of where this could shed some light on your model. So this takes a little bit to run. But while this is running, remember that what does our model do? Our model says something like, when I learn the value of this feature, it generally increased the model's prediction of your likelihood of buying an umbrella policy by a certain amount. So here, this is for median household income, right? So this is based on your zip code. So when each dot represents a particular data point in the test set. And what this means is when I learned someone had a high household, lived in a zip code with a high household income, it generally increased, always in this case, increased my the model's perception of their probability of buying an umbrella policy. So on the log odds scale, it increased it by about 0.3. But you see there's some vertical variation. Sometimes it was more, sometimes it was less. And the reason why it's more or less depends on the values of some other variables. So other variables might say, normally this would really increase my perception. Normally, when I learned you lived in a rich zip code, it would increase your probability by a lot. But now that I know this other thing, maybe it made the impact of the household income a little less or a little more. And this is where interactions come in. So the more vertical dispersion there is, that means there is more interaction effects, meaning learning this bit of information could have a variety of impacts on the model's probability, depending on the values of the other variables. And exploring this, you can get to some interesting insights. And here's one. It's a small effect, but it's interesting. Between median household income and the year of birth of the policyholder. So this is a kind of a sophisticated plot. So what we have is the median household income on the x-axis and the interaction value between the year of birth of the policyholder. So the way to think about this is, let's look at these 50,000s. These 50,000 things, sometimes you're closer to minus 0.2, sometimes you're a little closer to minus 0.3. So this is when I learned that you lived in a lower income zip code. What did the model think of your probability of buying an umbrella policy? And you see that it's mostly around 0.2, but sometimes it was a little more and sometimes it was a little less. Sometimes it was more negative and sometimes it was not quite so negative. So this sheds some light on why, how did the year of birth impact whether it was more negative or less negative. And what the model finds here is that when the year of birth was low, when the year of birth was around 1945, 1950, so when the person was older, finding out they lived in a low-income zip code had a bigger negative effect than finding out that someone who was younger lived in a low-income zip code. And if you think about it, this kind of makes sense because, young people might live in a low-income zip code because they're young and rent is cheap, or that's where their friends live, that's where the nightlife is. And it's probably less indicative for a young person of kind of their assets than it is for an older person. When an older person lives in a lower income zip code, it probably means that they have less assets. Whereas when a younger person lives in a low income zip code, it's probably less likely to mean that. And it's a small effect, but it's something you could tease out from this plot. So it's a very sophisticated point, takes a lot to think through. But again, this shows how, one thing, as we conclude this talk, one thing I really want everyone to take home is that, these models are really a tool to understand the world. It's not just about getting a prediction. You really want to understand the world, understand what's going on, and be able to make some hypotheses and test them. And using these tools and digging into understanding and looking at the effects the model is picking up on can help you formulate these hypotheses, can help you understand what's going on, and you can go through an iterative process where you can really understand what's going on with the problem. And if you think about in this set, we start with the premiums, and then we saw how the adding in the state explained these interesting effects we were seeing and how premium related to buying a policy. And then actually when we put the coverages in, the premium didn't matter anymore. So all of these things can help you build up an understanding of what's going on in your data set. And whether you're working in a scientific domain or an industry domain, there are a lot of situations where, your end goal is to just understand the world better using the data at your disposal. And I think these tools really give you that ability. So thank you very much for listening. I'm on the Slack channel. Hopefully this hasn't been too awkward with the asynchronous nature of it. But thank you very much for joining. And just to wrap up, please rate the talk on the ODSC app. Check out and subscribe to my YouTube channel. I'd love to see people on there. You can also sign up at numeraschool.com. You can make an account there. I have live events sometimes through YouTube, and I have my own Slack channel that I use to do audience participation. So if you sign up at Numeristical, when I have these live events, you'll be added to the Slack channel. You'll be able to participate directly. I'm doing a live training for ODSC. It's a 4-hour workshop, so it's going to be similar to some of the stuff we've covered, but much more extensive. We're really going to start at the beginning with gradient boosting and understand how it works, and go into a lot of detail and do a lot of examples. So if you're interested in that, it's supposed to be November 10th. Please register. And if you find the ML Insights package useful, please consider giving it a star on GitHub. And again, thank you very much. Have a great day.